we turn our attention to electric circuits. In this video, we'll start with circuit components that have algebraic models and examine some simple circuits containing these components. Then in the next few videos, we'll get to the components with differential equation models. We'll start with the simple circuit shown. Electric current consists of electrons flowing in a wire and is measured in amps, where 1 amp is the flow of 1 coulomb of electrons per second, and a coulomb is 6.24 times 10 to the 18th power, but who's counting? By convention, electron flow represents negative current, which flows from low voltage to high voltage, and positive current is the negative of negative current and flows from high voltage to low voltage. In normal usage, current means positive current, so it's opposite to electron flow. The force that pushes the current through a wire is voltage, measured in volts. Batteries supply fixed levels of voltage. A flashlight battery supplies 1.5 volts. A copper wire presents essentially zero resistance to the flow of electrons. A resistor is a component that does resist the flow of electrons. The resistance of a resistor is measured in ohms. For example, a tungsten filament in a flashlight bulb resists the flow of electricity, and electricity flowing through the filament creates heat and light and consumes energy, and hence some force is required to push the current through the filament. The resistance of a typical flashlight bulb is 5 ohms. Circuits are represented graphically by circuit diagrams with conventional symbols for batteries, wires, switches, and resistors. This is the circuit diagram corresponding to the flashlight circuit on the previous slide. The model for a resistor is given by Ohm's law, which states that the current through the resistor equals the voltage applied to the resistor divided by the resistance of the resistor, or I equals V divided by R, where I is current in amps, V is voltage in volts, and R is the resistance of the resistor in ohms. In this circuit, when the switch is closed, current flows from the positive terminal of the battery, through the wire to the switch to the bulb, through the filament in the bulb, and through the wire back to the negative terminal of the battery. The amount of current is determined by Ohm's law, that is, the resistor model. The voltage applied to the resistor terminals is 1.5 volts. The resistance of the resistor is 5 ohms, and so the current through the resistor is given by I equals V divided by R equals 1.5 divided by 5 equals 0.3 amps. In this circuit, positive current is flowing clockwise, while the electron flow is in the opposite direction. If we add batteries and resistors to the circuit, the battery voltages add and the resistances add. Note that the battery terminals have physically determined polarities. One terminal is positive, one is negative. So when we add them to the circuit, we must take polarity into account. So let's discuss polarity. Which current direction in the circuit, clockwise or counterclockwise, is positive? The answer is that we can consider either direction as positive. That is, we can and must choose a positive direction. In this circuit, we'll choose clockwise current as positive, as indicated by the arrow in the upper left corner of the circuit diagram. Since the voltages on both batteries are pushing the current in a positive clockwise direction, their voltages add. The resistors do not have polarities and their resistances add, so Ohm's law becomes I equals V1 plus V2, the sum of the voltages, divided by R1 plus R2, the sum of the resistances, and the answer is again 0.3 amps. If we reverse the direction of one battery so that it is pushing current in the negative direction, Ohm's law becomes I equals V1 minus V2 divided by R1 plus R2, and V1 and V2 cancel out, so the current is 0. Finally, we can add any number of resistors and batteries to the circuit, and by taking the battery orientations into account, Ohm's law will give us the current flowing in the circuit. Note that in this circuit, positive current flows counterclockwise.